In this video, we're going to look at the alternative method for significance tests of the sample mean. That is the method that uses critical regions. So to begin with, let's have a look again and remind ourselves of the key steps in setting up a significance or hypothesis test by finding a critical region. As with the p-test, the first thing we must do is define the variables, and we must then state clearly the null hypothesis and the alternative hypothesis. Having stated clearly those two hypotheses, we've got to describe the test statistic and give its distribution on the assumption that the null hypothesis is true. We then need to state the significance level of the test and state whether the test is a one-tail or two-tail test. If we're just looking for evidence, the normal thing to use is a 5% significance level. If we're looking for strong evidence, then we would use a 1% significance level for the test. The next step is to calculate the critical region for the test, and the critical region for the test is the set of values of the test statistic that are so unlikely to occur if the null hypothesis is valid that the alternative hypothesis will be accepted instead. Step 5 then is to state the decision rule and then apply the decision rule to the data that we've been given. And we at this stage must give that conclusion in context. The decision rule then is to accept the alternative hypothesis if the value of the test statistic lies in the critical region, and if the test statistic does not lie in the critical region, then we should conclude there is insufficient evidence to reject the null hypothesis in favour of the alternative hypothesis. Okay, now the other big thing we've got to remember is the result that we saw from an earlier video, which said that if we take samples of n random observations from a population which is normally distributed with mean mu and variance sigma squared, and calculate the sample mean of our samples, then the sample mean is going to be normally distributed with a mean of mu and a standard deviation of sigma over root n, or equivalently a variance of sigma squared over n, which means that we can say that the sample mean x bar is normally distributed with mean mu and variance sigma squared over n. So let's look at our first example now. After a year's growth, the height of seedlings of a particular tree are normally distributed with mean 38 centimeters and standard deviation 2.8 centimeters. Fred Greenfingers has been experimenting with a new fertilizer treatment on a sample of 40 seedlings. We've got to find the critical region for a significance test to determine whether this new treatment has produced an increase in the mean height of the seedlings after a year's growth. And when we've done that, we've then got to say what conclusion would be made if after a year's growth the mean height was 38.9 centimeters. And we also need to think about any assumptions that have to be made in order to conduct this test. To find the critical region for significance test, we need to set the significance test up properly. So the first thing is to define our variables, and in this case we're going to let mu be the mean height of the seedlings after a year with the new treatment. Now we don't know the accurate value of mu. What we are though trying to decide is whether from the significance test we can decide that mu is probably still 38 centimeters, or whether mu has increased from 38 centimeters. So we need to set up our null hypothesis and our alternative hypothesis. The null hypothesis is going to be that mu equals 38 centimeters. Remember, the null hypothesis has got to be an exact statement that mu takes an exact value, and the only exact value we could have for mu at this stage is 38. The alternative hypothesis is going to be that there's been an increase produced by the fertilizer, in other words, that mu is bigger than 38. We now need to state the test statistic and give its distribution on the assumption that the null hypothesis is true. Well, the test statistic is the mean height of a sample of 40 seedlings after a year's growth with the new treatment. Now, provided we assume that the 40 seedlings are a random sample and that the new treatment does not alter the standard deviation of the heights after a year's growth, then if the null hypothesis is true, we can say that the sample mean x bar is going to be normally distributed with a mean of 38 and a variance of 2.8 squared divided by 40. Okay, so that is x bar is normally distributed with a mean of mu and a variance of sigma squared over n. So if the assumptions in the blue box are true, and if the null hypothesis is valid, then we've got x bar is normally distributed with a mean of 38 and a variance of 2.8 squared over 40. We must now state the significance level of the test and whether the test is a one-tail or a two-tail test. Since no significance level has been specified in the question, the normal thing is to carry out a 5% significance test. Because we're only interested in whether there is an increase in the average height of the seedlings with the new treatment, we're only going to want to accept the alternative hypothesis that mu is bigger than 38 if the value of x bar is significantly bigger than 38. So it's going to be a one-tail test. So our next step then is to calculate the critical region for the test. Now, remembering that we know that if the null hypothesis is valid, then we're modelling the sample mean by the normal distribution with a mean of 38 and a variance of 2.8 squared over 40. The critical region for the test is going to be the values for which x bar is greater than c, where the probability that x bar is greater than c is 0.05 when the null hypothesis is valid. Now, when we're using the calculator, we need to remember that we need to use left-hand tails rather than right-hand tails. So the probability that x bar is greater than c is 0.05 is the same thing as saying that the probability that x bar is less than c is 0.95. We know that the distribution that we're dealing with has got a mean of 38 and the standard deviation of the sample mean is 2.8 divided by root 40. And both of those things are true if the null hypothesis is valid. So using the inverse normal on our calculator, we can get that C must be 38.728. So the critical region is the sample mean being bigger than 38.728. So we can now go on to the next part of the question, which says what conclusion would we make after a year of growth these plants with the new treatment had a mean height of 38.9 centimeters. So we need to state the decision rule for the test, and the decision rule for the test will be to accept the alternative hypothesis if the value of the sample mean is in the critical region, i.e. is bigger than 38.728, otherwise conclude that there is insufficient evidence to reject the null hypothesis in favour of the alternative hypothesis. The value of x bar that we had in this case was 38.9, So this is in the critical region, so we should certainly reject the null hypothesis in favour of the alternative hypothesis. So in context, we should be saying that the experiment gives significant evidence at the 5% level to accept the idea that the new fertilizer treatment does increase the mean height of the seedlings after a year's growth. What assumptions do we need to make? Well, we already have said that we've assumed that the sample of seedlings was a random sample which was treated with the new fertilizer, and we've also assumed that the treatment with the new fertilizer didn't change the standard deviation of the heights. For our second example then, we've got a medical textbook claims that the heights of 11-year-old boys in Wales are normally distributed with a mean of 140 centimetres and a standard deviation of 5 centimetres. A statistician wishes to test whether the mean is correct by taking a sample of 50 11-year-old boys. Prepare a 1% significance test for the statistician by finding the critical region, and state the conclusion she will draw if the mean of her sample turns out to be 142 centimetres. We need to set up our significance test, so the first thing we must do is define any variables. So let's mu be the actual mean height of Welsh 11-year-old boys in centimetres. Our null hypothesis then is going to be that mu is 140. In other words, the textbook is correct. Our alternative hypothesis is going to be that the textbook is incorrect. In other words, that the value of mu is not equal to 140. The test statistic that we're going to use is x bar, which is the mean height of a random sample of 50 11-year-old Welsh boys. We must now state the distribution of the test statistic, or x bar, under the assumption that the null hypothesis is true. In order to do this, we need to make a couple of other assumptions, namely that we've got a genuine random sample, and secondly that the textbook is correct in saying that the distribution of heights is normal, and that the distribution of heights has a standard deviation of 5 centimetres. If that is the case, then we can say that if the null hypothesis is true, then x bar will be normally distributed with a mean of 140 and a variance of 5 squared divided by the sample size, which is 50. So here is, if you like, a picture of the distribution of the sample mean if the null hypothesis is valid. Now, the significance level for the test is 1%. That's given to us in the question, and it is a two-tailed test because the alternative hypothesis is mu is not equal to 140. So we'll want to accept the alternative hypothesis if the value of x bar is much greater than 140 or much smaller than 140. So we've got a 1% two-tailed test. The critical region then is going to be in two parts. Each part has got to be half of the 1%. So we're going to have 0.005 as the probability for the two tails that we've got. So the critical region is going to be x bar is bigger than C1 or x bar is smaller than C2, where the probability that x bar is bigger than C1 is 0.005 and the probability that x bar is smaller than C2 is 0.005. Now we're going to find C2 first, simply because it's a left-hand tail rather than being a right-hand tail. So if the null hypothesis is true, then we've got the mean of the sample mean is 140. The standard deviation of the sample mean is the square root of 5 squared over 50. In other words, the square root of 25 over 50. In other words, 0.707. Using the calculator, the inverse normal functions on the calculator, we can see that the value of C2 is going to be 138.17. Since the distribution of the sample mean is symmetrical about 140, we can say that the value of C1 is going to be 141.83. So the critical region is the sample mean is bigger than 141.83 or smaller than 138.17. So our decision rule is that if the value of the sample mean is bigger than 141.83 or smaller than 138.17, then there is evidence at the 1% significance level to accept the alternative hypothesis. Otherwise, there is not sufficient evidence to reject the null hypothesis in favour of the alternative hypothesis. The value of the sample mean we had in our sample was 142 centimetres. This value of the sample mean is in the critical region. So we should conclude that there is evidence at the 1% level that the mean value of the heights of 11-year-old Welsh boys is not 140 centimetres. Which is better, doing a p-test or a critical region based test? Well, there are advantages and disadvantages in both. The p-test method is slightly shorter, but has to be redone each time a new sample is taken. On the other hand, critical region method, once you know what the critical region is for a test and stated the decision rule clearly, a test can be used over and over again by somebody who doesn't understand the technicalities of a significance test. Another advantage of critical region method is that if we want to do any error analysis on the significance test, then you need to know what the critical region is. But as we've already hinted before, the disadvantage of critical region method is it's slightly longer than the p-test method if you're just doing a single test. To finish this video off then, there is an example here for you to do. So pause the video, have a go at this example and take your solution along to your next lesson. And in the next video, we'll be having a look at Type 1 and Type 2 errors for significance tests using the sample mean.